October 29th, 2025. At the exact moment 3I/Atlas reached perihelion, the most watched interstellar object of the decade vanished behind the Sun. Earth's entire arsenal of telescopes blinded when history could happen. While the world missed it, Harvard's Avi Loeb released rapid-fire space-based evidence of a sudden brightening and unnatural blue tint. If 3I/Atlas really is doing something impossible today, what did we just miss? And what will these first images reveal? At 7:47 a.m. Eastern, the clock struck perihelion for 3I/Atlas, a moment so anticipated that astronomers worldwide had set alarms, only to be left staring at a blank solar glare. Every ground-based telescope on Earth was rendered useless, the comet hidden in perfect alignment behind the Sun. The world waited, knowing anything could have happened in those unseen minutes. A sudden breakup, a flare, or something no one had imagined. While the planet's best eyes blinked, Avi Loeb stepped forward with new evidence. His team released a series of stacked images from 3 space-based instruments, Stereo A's HI1 and COR2, SOHO's LASCO C3, and the GOES-19 CCOR1 coronagraph. These were the only tools capable of piercing the Sun's blinding curtain. In their processed data, Loeb's group reported a rapid increase in brightness as 3I/Atlas neared perihelion, paired with a striking blue color that stood out against the expected spectrum for comets. The details came fast. The object brightened sharply in the final hours, and color indices shifted toward the blue end, all according to Loeb's internal analysis. No independent teams have confirmed these measurements, and the raw photometry and calibration methods remain unpublished. Still, Loeb's claims have set the tone for the coming debate. He assigns a LOBO scale rank of 4 to the event, his own system for weighing the odds of artificial origin, suggesting the data is strongly suggestive, if not conclusive. The first hard numbers from space have landed, and the mystery of what happened behind the Sun is only deepening. Earth's telescopes were powerless to track 3I/Atlas. At the moment it mattered most, the problem wasn't just bad luck, it was geometry. In late October, the comet's path placed it almost exactly behind the Sun from our point of view, a phenomenon called solar conjunction. The angular separation, or solar elongation, dropped so low that even the most advanced ground-based observatories faced a wall of daylight and solar glare. No amount of optical or infrared sensitivity could overcome the Sun's overwhelming brightness. This alignment didn't just block visible light, it erased any chance for radar imaging, the gold standard for mapping distant objects. If Earth had been on the opposite side of its orbit, 3I/Atlas would have passed within about 54 million kilometers, close enough for planetary radar to send a signal, receive a reflection, and build a detailed shape model. Instead, the actual minimum distance is set for December 19th at roughly 269 million kilometers. At that range, even the largest radar dishes can't return a usable echo. The opportunity to scan an interstellar object with radar, something achieved only for a handful of comets and asteroids, vanished with this year's orbital arrangement. The result is a permanent gap in the record. No direct shape, spin, or surface data from radar. No high-resolution spectra from ground-based arrays at perihelion. Only the limited vantage of space-based solar observatories remains, relying on coronagraphs and heliospheric images that were never designed for this kind of detective work. The world is left inferring the most critical moments of 3I/Atlas's journey from a trickle of indirect signals, with the best observational tools sidelined by the simple mechanics of the solar system. Avi Loeb has assembled a catalog of 8 features he calls improbable for any natural comet. He presents each as a piece of a statistical puzzle, arguing that their combination strains the limits of chance. First, the trajectory. 3I/Atlas follows a path almost perfectly aligned with the ecliptic, the plane of Earth's orbit, a configuration he calculates at just 0.2% likelihood for a random interstellar visitor. Next, a jet observed in July and August pointed directly toward the Sun, not away as with most cometary outgassing. The object's sheer scale stands out as well, over 5 kilometers in diameter with a mass exceeding 33 billion tons and a velocity at perihelion near 68 kilometers per second. Its timing is equally peculiar, skimming close to Mars, Venus, and Jupiter, yet avoiding any close approach to Earth and reaching perihelion while hidden from every ground-based telescope. Spectroscopy adds another anomaly. Gas rich in nickel but poor in iron, with a high nickel to cyanide ratio that's rare among comets. Water content is unusually low, less than 4% by mass. In polarized light, the object displays an extreme negative polarization, stronger than any solar system comet measured to date. Finally, its inbound direction lies within 9 degrees of the famous WOW signal, a region of sky linked to a historic unexplained radio burst. Loeb contends that the odds of all 8 anomalies appearing together in a single object fall below 1 in 10 quadrillion. This statistical argument is his foundation for considering an engineered origin, and it sets a high bar for natural explanations. The sheer scale of 3I/Atlas sets it apart from almost every comet known. With a minimum diameter greater than 5 kilometers, its nucleus outweighs 33 billion tons, making it 100 times longer than SpaceX's Starship and vastly more massive than any human-made object. Its estimated rotation period, about 16 hours, falls within the range for large solar system comets, offering no immediate sign of artificial stabilization or engineered spin. These numbers alone invite AWE, but they also demand caution. Mainstream comet scientists point to the familiar physics seen in the data. By late August, 3I/Atlas developed a classic anti-solar tail, dust and gas streaming away from the sun, exactly as expected from natural outgassing. The sun-facing plume observed in July and August, highlighted by Loeb as unusual, is explained by the geometry of sunlight striking volatile-rich patches on a rotating nucleus. Such plumes have been documented in other comets when jets erupt from sunlit areas, sometimes appearing to point toward the sun from certain perspectives. Skeptics also raise concerns about measurement and calibration. Claims of rare nickel-rich, iron-poor gas and extreme color shifts rely on custom-processed data that hasn't been independently verified. Instrument teams emphasize that coronagraphs and heliospheric images were never designed for precise comet photometry. Without peer-reviewed reductions and cross-checked calibrations, even dramatic signals can be artifacts of processing or background subtraction. The debate now pivots on what can be tested. Extraordinary size and oddities in tail direction are intriguing but not unprecedented. Only future observations, especially independent quantifiable measurements, can decide whether 3I/Atlas is a natural comet with quirks or something truly out of the ordinary. Researchers are now on alert for any sign that 3I/Atlas is more than a comet. Radio observatories, both professional and amateur, are preparing to scan the object's path for unexpected transmissions as soon as it clears the sun's interference. The search list is clear: artificial radio bursts, sudden course changes, flashes of light, or unexplained heat. Each could suggest engineered activity. While no coordinated global campaign has been announced, SETI teams and planetary radar groups are quietly watching their windows. At the same time, calls for transparency are growing louder. Some in Congress, including Representative Anna Paulina Luna, have urged NASA to release any high-resolution HiRISE images taken before perihelion for public review. The push for open data reflects a new urgency. Every dataset, every signal could tip the balance. The next phase depends on what emerges from both the sky and the archives. In November, 3I/Atlas will return to view in the evening sky, with its path arcing through Virgo and Leo as Earth's vantage improves. The comet will be under intense scrutiny. Hubble and the James Webb Space Telescope are cued to capture high-resolution images and spectra, while ground-based arrays will monitor for changes in brightness, structure, or color. At perihelion, the nucleus endured roughly 770 watts per square meter of solar heating, enough to trigger fragmentation in a fragile natural object or, if engineered, to prompt maneuvers or controlled releases. Each instrument will target a specific signal. Radio telescopes listen for transmissions, infrared arrays seek excess heat, and optical observatories chase sudden flares or course shifts. The next weeks offer a clear decision tree, with every dataset a potential answer to the question still hanging over 3I/Atlas. At 7:47 a.m. Eastern on October 29, 2025, 3I/Atlas reached perihelion, hidden behind the Sun and unobservable from Earth. Space-based instruments like Stereo A and SOHO provided rare images showing rapid brightening and a blue hue, but crucial ground-based data was lost due to solar conjunction. Avi Loeb's team identified 8 anomalies, citing a cumulative probability of less than 1 in 10 quadrillion for a purely natural origin, while many astronomers point to known comet behavior, such as sun-facing outgassing and the development of an anti-solar tail, as plausible explanations. The object's minimum diameter, over 5 kilometers, and mass, exceeding 33 billion tons, set it apart from previous interstellar visitors. As 3I/Atlas re-emerges into the evening sky, Hubble, JWST, and radio telescopes are preparing to test for technosignatures, including maneuvers, probe release, and artificial signals. The release of key HiRISE images remains pending, reflecting ongoing debates about transparency. For now, the origin of 3I/Atlas remains unresolved, but the evidence gathered in the coming weeks will be decisive.